Here are solutions to homework set number 5 for ECE 461-661. The first problem is block diagrams. Given this block diagram, find the transfer function from x to y. Now there's a couple ways to do this. One is the shortcut. Take the gain from x to y, and there's one path right here, ABC, that goes in the numerator, divided by the loop gains. In that case, here's one loop, ABD, here's another loop, DCF, BCF. So that'd be my answer. That's one way to do it that usually works, and a lot quicker. The long, painful, but always accurate way is to label each summing junction. And this one actually doesn't do anything, so I didn't label it. And then write the equations. So M is x minus dBn. N is a times n minus f times y. And y is c times b times n. Now doing some algebra, I can substitute in for m to get this equation. Now solve for n, then substitute. N goes here. And after a little bit of algebra, clear the denominator, bring all the y's left, I get the same answer. So that's problem number 1. Problem 2, find the transfer function from x to y. Again, using the shortcut, what I would do is, here's the path from x to y, A, B, C. That's one path. Here's another path, D, B, C. And here's another path, EC. So there's the numerator. The loop gains. Here's one loop. It's 1 plus the loop gains, BF. Here's another loop, A, B, C, G. That's it. So that'd be my answer using the shortcut. Doing it the long way. Label each summing junction, and then write your equations. M is x minus g times y. N is d times x plus a times m minus fbn. P is b times n plus c times x. And y is c times p. Now, let's simplify. Substitute in for m. Gives you this equation. Solve for n. Now I'll take n and plug it in right here. Solving for p. And then substitute p in here. C times p is y. Now clearing the denominator, bringing all the y's left, here's my answer. And it's almost the same. I've got 1 plus bf plus abcg, 1 plus bf plus abcg, just rewritten. And the numerator, EC, right here, dbc, abc, there it is. I have this extra term, FBCE. So there apparently is an extra term. It's F, it goes E, C, FB. I don't see it, but it is there. So the long way always works. The shortcut usually works, but occasionally miss a term. Okay, problem 3. Here's a transfer function. Express it in 2 different canonical forms. So one approach is to multiply it out, put this in controller canonical form, in which case the denominator polynomial goes right here with a minus sign. The numerator polynomial is your C matrix, and there's your B matrix. That's one form, controller form. A second form is transpose it, and I have your A transpose, C transpose, B transpose. That's a perfectly valid answer. Third form. I can't really do cascade form since the poles are complex, but what I can do is factor this into a real pole and a complex pole. Here's your real pole in controller form. Here's the complex pole in controller form. And the first system feeds the second system. Here's the 2. So this guy feeds the second system. There's your B matrix for controller form. And then my output is S plus 10. So that's your C matrix in controller form for this guy. And there's an infinite number of other solutions. Basically, there's an infinite number of ways to represent a system in state space. They're all equivalent. They're all perfectly valid. Problem 4. This is where state space is really useful. Find the transfer function from V0 to V3. Now, what you did back in Circuits 2, Signals and Systems works. It's kind of painful. State space makes this a whole lot easier. What I'll do is my energy storage elements are the capacitors. And the equation I'm going to be using is I is equal to C dV dt. So if I define the current through the capacitors, I know the derivative of the voltage. Those are my differential equations. So the first capacitor, I1 is C dV dt. That's equal to this current, V0 minus V1 over 10, plus this current, 0 minus V1 over 100, plus this current, V2 minus V1 over 20. Add I2. I2 is equal to this current, V1 minus V2 over 20, plus this current, 0 minus V2 over 150, plus this current, V3 minus V2 over 30. And the third one, I3, is this current, V2 minus V3 over 30, plus this current, 0 minus V3 over 200. Gives you 3 equations. If I divide by C and group the terms, I wind up with that set of equations. That I can put in state space form. So the first equation, SV1, I'm going to group the states as V0 or V1, V2, V3, and the input is V0. So here's the gain times V1, V2, V3, and V0. SV1 is 33V0 minus 53V1 plus 16.67 V2. Second equation, 25V1 minus 45V2, 16.67 V3. Third equation, 33V2 minus 38V3. And my output is V3. So here's my A matrix, my B matrix, C matrix, and D matrix. Usually the D matrix is 0. Not always, but usually. Now to find the transfer function, I switch to MATLAB. In MATLAB, I input the A matrix, the B matrix, C and D, input the system in state space form, then find the transfer function. So there you are. That's the gain from V0 to V3. Problem 5 says if I change my output, instead of measuring V3, I measure V1. All that changes is change the C matrix. I'm now looking at V1. Now find the transfer function, and note, the denominator polynomials are the same. The denominator determines how the energy decays. Changing what you're measuring doesn't change the energy in the system. The numerator does change. What the numerator tells you is how these energy states combine to give you the output. That's one of the reasons in this class we only pay attention to poles. It's kind of worst case. If I want to know the settling time, I would say the settling time is 4 over the dominant pole, over 12.87. And that's kind of worst case. If the total energy decays in 4/12 of a second, then whatever I'm measuring also decays in 4/12 of a second, or faster. Saying or faster, I could have pole zero cancellation, in which case this becomes a dominant pole. But worst case, that's your slowest pole. Problem 6. If I have an RLC circuit, repeat. And here what I'm going to be doing is using 2 sets of equations. I have I is C dV dt. That's for capacitors. And for inductors, I have V is L di dt. So the energy states are the voltages on the capacitors, V1, V2, V3, and the currents through the inductors, I4, I5, I6. Starting with the capacitors, I1 is C dV dt. I1 is the current in, I4, minus I5, minus this current, minus V1, minus V3 over 10. I2 is the current in, I5, minus current out, I6. I3 is the current in, I6, plus V1 minus V3 over 10, minus this current, minus V3 over 100. That's the capacitors. Now for the inductors. The voltage across this inductor on the left is V0 minus this voltage, and that's I4 times 10. So there's the voltage on the left. Voltage on the right is V1. Second inductor, voltage on the left is V1 minus 15I5. Voltage on the right is V2. So here's voltage on the left, voltage on the right. Inductor 3, voltage on the left is V2 minus 20I6 minus V3. So those are my dynamics. If I solve for the derivatives, divide by these numbers, group the terms, I get 6 equations. Those are the dynamics for the system. In state space form, I'm going to put the states as V1, V2, V3, I4, I5, I6. SV1 is 50 times I4 minus 50 times I5 minus 5V1 plus 5V3. Likewise the second, and so on. So here's my A matrix. There's my B matrix. If I want to find the transfer function to V3, again this is your V1, V2, V3, I4, I5, I6. If I'm looking at V3, there's my C matrix. Input the A, B, C, D. Throw into MATLAB as in state space form, find the transfer function, and there she is. Because the MATLAB is really convenient for this, state space makes this type of problem a whole lot easier. Problem 7 asks, what initial condition makes the transient decay as quick as possible? What makes the decay as slow as possible? This is really an eigenvector problem. If I find the eigenvalues, eigenvectors of A, here's the eigenvectors, here's the eigenvalues. Is a 6 by 6 matrix, I've got 6 eigenvalues, I've got 6 eigenvectors. Note that the eigenvalues are the poles. Here's your slow pole, here's a slow eigenvector. So this is the one that decays slowly. And here's your fast pole, and the fast eigenvector. What that says is that if I make this my initial condition, pull off the first eigenvector, that's all rows, first column, take the first eigenvector, scale it, so this term is 1. If that's my initial condition, here's your V1, V2, V3, I4, I5, I6. This will decay as e to the minus 1.05t. And that kind of makes sense. I have basically 3 voltages, no currents. So if I take this circuit, raise all the voltages, and then slowly the currents go to 0, or the voltages go to 0, as e to the minus t. That's the slow mode. The fast mode is pull off the 5th eigenvector. Pulling that off, scaling it, so here's your V1, V2, V3, I4, I5, I6. Here I've got big currents. This is 6 amps, 9 amps, 2 amps with minus signs. If I make the currents large, very quickly the energy goes to 0. And again, that kind of makes sense. If I have large currents, large initial conditions on the capacitor, large currents, then very quickly the energy gets dissipated by these resistors. So that's the idea of eigenvalues, eigenvectors. Eigenvalues are kind of important. Eigenvalues tell you how it behaves, e to the minus t, e to the minus 50t. Eigenvectors tell you what behaves that way. This mode decays slowly, this mode decays quickly. And then I've got the other modes as well. In fact, this one's going to oscillate, complex poles. But that's homework set number 7 for ECE 461.